Today, we're going to talk about differentially private machine learning. Usually when we talk about machine learning, the primary concern is accuracy, that is test accuracy on the test dataset. Well, today we're going to be talking about another concern, namely, what do we do if the training dataset is sensitive? We want to make sure that whatever machine learning algorithm we run does not leak information about that training dataset. So today we'll talk about, first, some things that can happen which result in data being leaked during the training process. Next, we'll talk about a notion, a definition, which helps us avoid this, known as differential privacy. And then finally, we'll talk about a sort of plug-in method that allows us to privatize pretty much any machine learning algorithm, known as differentially private stochastic gradient descent. Okay, without further ado, let's start. First, let's talk about the Netflix prize. The Netflix prize, I'm sure all of you are familiar with Netflix, but the Netflix prize was a recommendation engine competition. So by a recommendation engine competition, I mean that you know that Netflix and a lot of systems online have recommendation engines. That is, given things you've watched in the past or content you liked in the past, what will you like in the future? So this was in the comparatively early days compared to the current state of the art, where they in 2006 said, okay, anyone who can significantly improve the performance of our recommendation engine, or whoever can improve it the most, will win a $1 million prize. So naturally, a lot of different teams participate in this, trying to claim a share of the prize and the glory. And yeah, there was a success in the sense that a lot of teams participated, and there were indeed significant improvements to the algorithm. Now, how do you run such a recommendation engine competition? Well, in order to make predictions about what users will like to do in the future, you'll of course need some training data in terms of data about what people have done in the past. So naturally, Netflix, they provided some training data. In particular, they provided tuples, 4 tuples, which had basically an anonymized user ID, the movie they watched, what rating they gave this movie, and what date they watched this movie. So why did they anonymize it? Well, it's kind of sensitive data. Your movie watch history might be something you don't want shared with the world, especially without your consent. So naturally, Netflix took some best effort approaches in order to prevent this type of violation. That is, namely, if your movie, if a tuple would be associated with your real name, they just replaced you with some fixed identifier that doesn't really say what your real name is. So my name, Gautam, would be perhaps replaced with a number 1, 2, 3 or something. So it seems like my identity has been lost in this data set. However, this is a rather naive form of anonymization, and actually it doesn't really work, especially in this case. And why is that? Well, there's sometimes some clever types of attacks that you can do which will allow you to still recover the sensitive data. So what was done in a result by Narayanan and Shmatikov in 2008 is they showed that actually it's possible to cross-reference this information with public IMDb data. Public IMDb data, if many individuals choose to write reviews under their real name, which also give a movie, a rating, and a date. So basically, just by cross-referencing these two data sets, finding if a movie was rated on a particular date and it got a similar rating in both the IMDb dataset without the user's name and the public IMDb data where maybe they didn't provide their real name, then you can connect them up. So displaying in a sort of type of picture here, you can see an image of what might have happened. So this is a caricature by Arvind Narayanan, but it kind of identifies, demonstrates the nature of the attack. So you can see we have this public incomplete IMDb dataset, which shows which movies certain individuals liked, for example, Alice, Bob, and so on. These are what they liked and what they didn't like. And you can imagine that based on the anonymized Netflix data, this is sort of going to resemble this thing on the right. It's not going to be perfect. It's going to be a little bit noisy. For example, someone might not have reviewed a certain movie on IMDb where they did on Netflix, or vice versa. There might be some differences, but generally there should be a strong correlation between individuals posts on IMDb and Netflix. And based on this, you can kind of match up which individuals correspond to which histories. Now, this is not, you might be thinking, what's the big deal? Okay, if they chose to post publicly about what movies they watched and what they reviewed, then so be it. That's their prerogative, and this shouldn't be really a privacy violation. However, this is not the end of the story in the sense that maybe they were okay with revealing the fact that they watched a few different movies, but there was one movie they chose specifically not to write a review about, something which is sensitive, for example, on sensitive political topics or something like that. So maybe there's some of their watch history that they wanted to keep private by not posting publicly, but now, because of the release of this Netflix dataset, they could be identified from that. And in fact, under US law, this was run in the US, this actually is considered to be a violation of users' privacy. There's specific laws which prevent release of an individual's, say, movie rental history in sort of a brick and mortar real movie history store, when this law was a movie store when this law first came out. But basically it was thought to be applicable in this setting as well, and therefore there was a big legal dispute about this, and in fact it resulted in a class action lawsuit and cancellation of the sequel, Netflix Prize 2.0. So this is just supposed to demonstrate that a kind of best effort anonymization approach often doesn't work on real data sets, and you have to be more careful, because clever attacks like this can come along which are blatant violations of people's privacy. Okay, so that's one example. Let me give you another example, and this is perhaps more relevant directly to machine learning, where there's an interesting phenomenon of memorization in neural networks, and I'm going to be talking about in this slide a paper by Carlini, Liu, Erlingson, Kos, and Song. There's also a more recent paper by Carlini et al., which I'm not going to talk about, but this second paper kind of shows similar types of memorization phenomenon going on in these large language models that are so popular now, like GPT-2. You should check it out. Check out the paper if you're interested, but I'll just focus mostly on this just to illustrate. So the setting that I'm going to discuss in this slide and where privacy violations can happen is that of language models. And it turns out language models can strongly memorize a lot of the training data that is fed into it. Now, the question is, how do we quantify and measure this? That's essentially what we'll discuss. So first of all, there's the log perplexity of the sequence, which is defined as the following. So this might be a bit of an arcane quantity. Think about it for a bit and maybe parse what it means. It just says kind of what is the, how unlikely is a sequence. So a sort of a high number here, a large log perplexity, if you just sort of reason it out, you'll see that it's a high perplexity corresponds to a sequence which has a low probability. So for example, and vice versa, of course. So for example, Mary had a little lamb. This is a sentence which could appear very natural in natural English. So we would assume that a language model would assign a low perplexity score to this sentence. However, if you have something like a correct horse battery stapler, then this is a sequence which is not really a proper English sentence, or not proper English phrase, which therefore would result in it having high perplexity. That is assuming this kind of model was trained perfectly and it knows perfectly what English is. Now, this all seems nice and natural, but now there might be some hiccups, some flukes in this whole thing. For example, what if correct horse battery staple actually appeared in the training data set? Now, there's the famous XKCD comic, which uses this as a phrase. So maybe this is something which is not valid English, but it's appeared in the training data now. So in that case, you'll say the language model, which we don't really know fully how it works, we might think that, okay, since this was in the training data, maybe it thinks that this is a real valid phrase and therefore it would assign a low perplexity score to it. So more broadly, the hypothesis that we have here is that this language model, which assigns a log perplexity to sequence, kind of lower if it's more likely and higher if it's less likely, you might have the hypothesis that things which are unlikely, which nonetheless appear in the training data set, they might have a low perplexity score anyway, kind of indicating that they're in the training data set. And how would you test this? Well, one way to test this is by kind of putting what are known as canary phrases into the training data set. For example, what you could imagine is, suppose you throw something kind of sensitive in, there's something sensitive in the data set. For example, my SIN number, my social insurance number, is whatever number it is. Suppose that perhaps your SIN number is truly in the data set in a format like this. Well, then it would have a, perhaps it would be revealed by the language model by having a lower perplexity score than it should. So what's a way of testing whether a neural network or a language model has memorized something of this format? Well, what you can do is, let's do a kind of thought experiment. Suppose that this is, it hasn't memorized anything, and it doesn't know what your social security number is. Like, let's suppose your security number, or your social insurance number is 1, 2, 3, 4, 5, 6, 7, 8, 9. If that were the case, then, if it hasn't memorized it, then any sequence of numbers you put in here should be roughly equally likely. That is, my SIN is 1, 2, 3, 4, 5, 6, 7, 8, 9 should be the same perplexity roughly as 0, 0, 0, 0, 0, 0, 0, 0, 0. Yeah, very roughly speaking, all possible sequences which are like this should be in a random order when you put them in a when you compute their log perplexity, then put them in a list from lowest to highest perplexity. So now a way to test if a particular phrase has been memorized is by putting it in the training data set. So for example, just putting in my SIN as 1, 2, 3, 4, 5, 6, 7, 8, 9, and seeing in the list of log perplexities of the output, seeing if that appears near the top. If it appears near the top, having a lower perplexity, that means that the neural network is indeed memorizing it. And therefore, that's a type of privacy violation. Because the way you could attack it is just by typing in all phrases of this nature, and then seeing which one is seeing which ones are near the top, and those are going to be indicated as more likely to be real SIN numbers. So here's a kind of plot from their paper showing what this does. So imagine a point is inserted in the exposure is just some kind of measure. I'm not going to define it formally, but it's a measure about how exposed the phrase is. That is, how much more likely is it to be at the top? How much more at the top of this list, showing that it's a low perplexity, is it, than from just being at a random place in the list, which it kind of should be if nothing is known about it, if it's sort of privatized. And you can so show that if there's 0 insertions, then it's not really very exposed. Yeah, there's no way you can tell that this is not really any more likely than it should be. But if you add this phrase to the training data set a few times, this is a relatively small language model, but if you start adding it to the training data, then after just a few insertions, it'll start to spit it out and indicate that this is actually part of the training data, thus being a violation of privacy. Interestingly, so it does seem like language models, if just trained naively, are going to memorize things. Standard techniques which are used in machine learning in order to prevent overfitting, like regularization and dropout, it seems like those don't really help the picture that much, and they still result in high exposure. But interestingly, differential privacy, which is kind of the topic of today's lecture, is the main strategy which did indeed work in terms of reducing the exposure. So good. I've talked to you about 2 different types of privacy attacks, and hopefully it should be clear why both of these are privacy violations. They reveal something about the training data which may be sensitive, and really, if we wanted a perfect machine learning algorithm, we didn't really need to reveal something like this. This didn't really have to come out. You know, a perfect language model would in fact not have revealed these secrets, because it's kind of saying this is more likely than it should have been. Good. So let's talk about a rigorous notion of data privacy, which allows us to kind of control the probability or control how much information is leaked in methods like this. And we're going to talk today about the notion known as differential privacy, introduced by Dwork, McSherry, Nassim, and Smith in 2006. I'm first going to tell you the kind of setup and how you can imagine a differentially private algorithm, and then we're going to discuss a little bit about the definition. So the kind of game that we're going to play here is we're going to imagine that we have some algorithm, and we want this algorithm to be differentially private. Differential privacy is a definition about an algorithm. We say an algorithm is either differentially private or not. It's not a property of data sets. It's not an algorithm itself. It's a property of an algorithm. So now, what do? We imagine that there's, say, one of two different data sets which differ in exactly one entry fed into our algorithm. So you can see x and x prime differ in one entry. And one of them is fed into this algorithm M. And this algorithm produces an output, and an adversary takes a look at this output. The adversary is trying to determine which was really fed into this algorithm. Was it x, or was it this other data set, x prime? And the idea is that if the adversary cannot make a significantly better than random guess about figuring out whether it really came from x versus x prime, then we say the algorithm is differentially private. So in other words, the adversary can't tell in particular whether this individual was in the data set or not. And therefore, if they can't even tell if an individual was in the data set or not, then they have no hope at all of telling whether anything more about this individual. So maybe intuitively you can see why that is a reasonable form of privacy. Now, a little bit more formally, let's say, let's define what differential privacy is. So an algorithm M, which takes in a data set over domain D over n entries and maps to, say, some set R for range. This is going to be epsilon delta differentially private if for all inputs x and x prime, which differ in one entry, so you can see these are data sets which differ in one entry, we have the following property. Now let's try to parse this. This is a little bit of a mouthful, and it never makes sense really the first time you see it for most people. And what does it say? It says for all subsets of the range, so for all kind of outcomes, all kind of indicators, or all events really, the probability distribution that the dataset, that the algorithm run on dataset X has of falling in the set is comparable to the probability that the algorithm when run on X prime has of falling into the set. So let me say it a different way. We're saying that the probability distribution of M on X is very similar to the probability distribution of M on X prime. And there's some we have to be a little bit more precise about what it means, like the probability of falling in some set, and what does it mean by close. We're going to define that in the next slide. But really, all I want, the main thing that you have to get out of this, to understand, is that the probability distribution on the algorithm on similar data sets is going to be similar in some way. If you get that, you get 90% of it. There's a little bit more in the definition, but that should be your main takeaway. And how do we quantify close-in distribution? Well, there's many ways one could do this, but the way that turns out to be right for differential privacy, and a lot of thought went into the definition, is the following type of way. So we have that the probability of some outcome happening under dataset when M is run on dataset X is less than e to the epsilon times the probability of the same event under when the data set is X prime, plus some little delta. Yeah, so this is a bit odd. Let's discuss, there's a few points which we have to discuss here about this, which we'll get to in a minute, and kind of unpack what some of these things mean. So yeah, this is differential privacy. And this was introduced in 2006, and it's seen a lot of critical acclaim, let's say, since then. It's seen use so far in practice at Google, Apple, and Microsoft, and perhaps one of the most impactful deployments to date will be in the 2020 US Census, where it's going to be used to make sure that when people fill in their census forms, that the results that they report are not going to reveal too much information about individuals in the dataset. And that's going to be run on, say, around 300 million Americans. So it's a huge deployment, and it's like there's a lot of implications of this. Some people are happy, some people are sad. There's in fact lawsuits going on about it. Yeah, that's right. There's lawsuits. The state of Alabama has filed a lawsuit right now about differential privacy in the U.S. Census. So this is getting pretty mainstream, let's say. Right. But let's these are sort of some practical deployments. It's also highly regarded as well in theory, winning a recent Gödel Prize, which is one of the top prizes in theoretical computer science. So let's comment a bit about the definition. There's these two parameters, epsilon and delta, and a question I get a lot of the time is, how do I set these parameters? What is a good value of epsilon and delta? Let's comment first about the fact that if you have epsilon and delta being equal to 0, then this is to say a perfectly private algorithm. These are going to be the exact same distribution, and no information at all about the data set is leaked. So that's kind of the strongest possible. So the lower epsilon and delta are, the more private it is. The higher epsilon and delta are the less private it is. In particular, say epsilon equals infinity. This will give you basically every algorithm you've learned so far. Delta equals 1 will also give you every algorithm you've learned so far, because these basically correspond to no privacy. But okay, though there's no privacy, what corresponds to good privacy? Well, I'd say very roughly speaking, a good privacy guarantee is, say, it kind of depends on your application and your setting, but roughly you can think of epsilon as being a small constant, something around 1, not necessarily exactly 1, anything between, say, 0.1 and 5 should be thought of as a reasonable privacy guarantee. And things outside those bounds you should be a little bit skeptical about, in my opinion. Just maybe try to think about whether it really makes sense or not, because imagine some people sometimes have epsilon to the 10, and e to the 10 is a huge multiplicative factor. That means the probability is being amplified a lot. So you really need to think of it whether it makes sense or not in those settings. And also, so this is going to be a small constant, and you should think of delta as being really, really small. Say at least smaller than 1 over n, where n is your data set size. The reason is because if it's around 1 over n, there's very simple but very not private algorithms that you can run. For example, like an algorithm that satisfies roughly 0, 1 over n differential privacy, that is where delta equals 1 over n, is a simple algorithm called, I guess I've heard it called name and shame, where you just pick a random person's data and output their data exactly. This is going to be like differentially private for delta equals 1 over n, but of course you can see picking a random person's data and outputting their data is not really the most private in a certain common sense way. So yeah, typically these are reasonable parameter settings that you want to think of delta as being pretty small. Let's see, other things to comment. This is a worst case guarantee. That is, we're not going to look at x and x prime being being with respect to some specific data set. It has to be really a property of all data sets which you could feed into the algorithm. Otherwise, it doesn't really make sense, and it's not as strong a privacy guarantee. You might be wondering why. So let me comment that this e to the epsilon, in many cases where epsilon is small, it can be replaced with 1 plus epsilon. We do it this e to the epsilon way just because there's certain cases where if you run 2 differentially private algorithms, if you change more than one individual, then you kind of want guarantees like this, where it'll be where basically putting things together in the exponent will be nice. And that happens nicely when you have this e notion, and it doesn't happen so nicely when you have just 1 plus epsilon. So this is for something called group privacy, which we'll come back to a bit later. You might be thinking, okay, this is an asymmetric definition, but it's actually symmetric because if you switch the role of x and x prime, then in fact this will be the same thing. You'll have the guarantee in both directions. And as a final comment on the technical notion of this definition, M must be randomized. Like there must be some randomness. You can't just have a deterministic algorithm which takes in the data set and outputs something deterministically. You can convince yourself of this. The only algorithm really which is not randomized is something which doesn't depend on the data, like say a constant function will essentially satisfy this just trivially because The distributions will be independent of the data. But besides that, generally M must be randomized. So these are some technical comments about the definition. But let's take a step back and talk maybe a little bit more big picture about what differential privacy really means. What does it guarantee and what doesn't it guarantee? Because this is a very common thing, because we currently, what do I want to say? Privacy is something we all have a common sense understanding of what privacy means, but differential privacy is a very specific type of privacy, and therefore it's not going to prevent all types of things which we might consider privacy violations, and it'll protect some things against some things which we don't consider privacy violations. So it's not a perfect match between the common usage of privacy and differential privacy. Essentially, I kind of said this before, but differential privacy says that the outcome of an algorithm is going to be the same whether or not your data is in the data set, in particular, one person's data in the data set. Nothing more, nothing less. Well, okay, I'm being a bit informal, but generally this is the gist of what it tries to say. The outcome is going to be similar. So what does this protect against? It protects against things like linkage and membership inference attacks. So a linkage attack is kind of what we saw in the Netflix example, where there's some external data set where you're trying to match people up one by one. So if the outcome, whatever is given, is the same whether or not your data is in the data set, then clearly there should be no way to link your individual information to some external data set, because it would be as if you weren't there. Similarly, I haven't talked about membership inference attacks. I guess it's the second can kind of be, the second example can kind of be seen as a membership inference attack, where essentially you're trying to see whether a specific point is in the training data or not. And similarly, differential privacy does indeed protect against that type of attack, just because that's literally what the definition says. Now, you have to be careful, though, because it doesn't always protect against things like, in particular, it does not preclude statistics in machine learning. Remember what I said a few slides ago, where if we had a perfectly accurate algorithm for the memorization example, that would in fact have been perfectly private, because it would have ignored, flukes in our training data, which said, okay, that this is kind of more likely than it should be. So differential privacy in statistics and machine learning, when done perfectly, are not contradictory, and you can do it. And there are some interesting consequences of this, which things that might feel like privacy violations, but at least in the definition of differential privacy, are not privacy violations. So for one common example is the smoking causes cancer example, where you imagine you're a smoker, and you don't, sorry, how do I want to say this? Suppose you are a smoker and you're asked, okay, do you want to participate in the study, which will try to match up whether smoking causes cancer or not? Well, you might think, oh, geez, I don't want people to know that smoking causes cancer, because if they knew that, then my smoking habit would reveal that I'm more likely to get cancer, and my insurance premiums would rise. So what you do is you decide to not participate in the study because you don't want to help that. But nonetheless, of course, the study is run, enough people participate, and it's found that indeed smoking causes cancer, and your premiums do rise. So in some sense, was there a privacy violation here? Well, some people might say that. But differential privacy would still allow this thing to happen, because whether or not, independent of your individual data about the fact whether you will particularly get cancer or not, there's still a fact about nature, and this is not precluded by differential privacy. Another simple example I'll mention is, for example, suppose you're wearing a cast. People are not likely going to infer, based on their past experiences and just based on society, that you have a broken bone. So there's sometimes indicators based on people's past experiences or other science that has been done, which is kind of independent of your data. And while you might think that this is a privacy violation, within the definition of differential privacy, at least, it's not intended to stop that. Right. So just to sort of succinctly summarize, sometimes machine learning can lead to something that feel like privacy violations, but that's not something really differential privacy is meant to stop against. And you have to think whether you want to run machine learning in the first place or not. But specific types of attacks, which are literally tied to individuals, are what it's supposed to protect against. And with that in mind, let me note that differential privacy does not say help when you need to identify specific individuals. By definition, this is not a thing that it can do. For example, disease contact tracing is something which you might have heard a lot of talk about, privacy-preserving methods. Well, that's not really the type of privacy that differential privacy is meant to really help it with. It's sort of more meant to deal with aggregate statistics, not when you need to find specific individuals. And the final comment about the definition is that this is an information theoretic notion. What do I mean by that? That means no matter how powerful the adversary is, how powerful the attacker is, even if they had a super strong computer, based on the information given out, then they still can't be able to cause a privacy violation. So this is a rather strong notion and is rather convenient. So okay, that's all we want to talk about philosophically about differential privacy. Let's talk about some properties of differential privacy. One of the reasons of the success of differential privacy is there's so many nice things about it, properties which make it very convenient for dealing with. So one of them, the first one we'll talk about, is post-processing. So suppose we have an algorithm which is differentially private, then any function of that output is also going to be differentially private. That kind of makes sense in the sense that if you put out something, then you can't sort of undo the privatization. That's sort of all it says. The next thing is group privacy, because all we've talked about at this point is two data sets which differ in one entry. Well, what if you have two data sets which differ in k entries? You want to have sort of these privacy guarantees for differences of data sets which differ in k entries, and you have the following very similar type of privacy guarantee. Sorry, this isn't actually quite perfectly accurate. In particular, I guess the main part that is important that I want you to focus on is accurate. This e to the k times epsilon, essentially, like I kind of indicated before, as you make the data sets further and further away, then you'll have a k times the epsilon instead of just this epsilon. There's also some change in the delta, which I somehow forgot to include here, but it increases quickly, but it's not the kind of main thing that maybe you want to focus on is this e to the k epsilon. And finally, perhaps the most important property of differential privacy is what's known as composition. So what we've discussed about is just running a single algorithm on a data set. But what if you run multiple algorithms on the same sensitive data set? This is, of course, very natural. You're not just going to run one. You're not going to go through all this work of gathering some data set and then just run one query and then call it a day. You're going to want to run multiple things on the same data set. So this is where composition comes in. So this says if we run, say, k different epsilon delta algorithms, then you can say that the overall running of these k different things on it, the overall transcript, all the outputs you produce, the result is going to be, first of all, it'll be k times epsilon, k times delta differentially private. This is a property known as basic composition. Kind of very intuitive, saying that the privacy guarantees kind of add up. The other thing that it says, this is like basic and not too hard to prove. A harder thing to show is something known as advanced composition, where you have this type of guarantee for any delta prime greater than 0. Now, don't worry too much about this. The main thing I want you to take away from this is the fact that instead of scaling linearly in the number of algorithms you run on the data set, this says you only have cost which increases as the square root of the number of algorithms you run. So you pay quadratically less in terms of your privacy loss, as it's called, in advanced composition. Cool. So those are the three of the main properties that differential privacy has. Keep in mind composition because it's going to be useful later, and essentially just this square root k thing here. Cool. So we've talked about this so far, that differential privacy is a definition. And if we have a definition, we need an algorithm which satisfies that definition. So I'm going to tell you just one algorithm which satisfies this definition. There's many algorithms, but just one of the simplest ones. Not the simplest one. The simplest one is what's known as the Laplace mechanism, but we're going to focus on something known as the Gaussian mechanism for reasons I'm not going to get into in this lecture. So the Gaussian mechanism is a standard tool of privatizing any sort of statistic, and it's essentially just add Gaussian noise. But it's not quite that simple because it's a quantitative notion. We have to be a bit more precise as to what we mean. So first of all, what we need is to understand, say, the sensitivity of a function. And this is the following definition. It's going to be, you take the difference between the function when applied to some data set x and the function when applied to some data set x prime, and you take the L2 norm of their difference. And you take the maximum of this over all x and x prime, which are neighboring. That is, again, differing in only one entry. So it's a very intuitive notion. How much can the data set change in the worst case if you change one entry in it? And here's a simple, like, illustration, a diagram. Imagine that you had a function whose L2 norm is bounded by c. So you say that the point lies somewhere in this ball. Well, then the sensitivity is going to be at most, say, 2c, because, maybe you move 1 point from here to here, and the function will change by a value of at most 2c in L2 norm. Right. So with this definition in mind, then we can define the Gaussian mechanism. I'll do it a little bit informally. Well, it's going to be very simple. You just let your private mechanism, or your algorithm, it's for whatever reason called mechanism sometimes, but you can just think of this as being synonymous with algorithm. So what you're going to do is you're going to take your function that you want to compute non-privately, and what you do is, say if it's k-dimensional, what you do is you add Gaussian noise to each coordinate of it. And what you do is, how big is this noise? Well, the noise is roughly going to be with standard deviation equal to the L2 sensitivity of the function divided by epsilon. That'll be your standard deviation. So the main thing is just appropriately calibrated noise to each coordinate. And remember that epsilon is a privacy parameter. I've hidden some log 1 over delta, which is not too important for at least for instructive purposes. But the point is, very roughly speaking, if you add noise calibrated to this amount to each coordinate where it's calibrated to the L2 sensitivity, then the overall result will be epsilon delta dp. Good. Yeah, so that's, again, the basic, simplest private algorithm, where you just take your non-private statistic and you add noise proportional to the sensitivity divided by epsilon. Okay, so this is a very useful tool, and differential privacy is usually built upon a few core tools in the toolbox, and given those tools, we can do a lot more with them. So let's see how to privatize a machine learning algorithm, namely stochastic gradient descent. So let's recall for the millionth time, perhaps, how what stochastic gradient descent is. In its most basic form, it can be described as the following. We're going to choose a random mini batch B of points from the data set. What we do is we then compute the average gradient. So we compute the gradient at each individual point at the current parameter vector theta t. And we average this over all points in this mini batch that we sampled and average it. And then we take a step in the negative direction of the gradient. That is, we basically say that theta t plus 1 is equal to theta t minus some learning rate times this quantity here. And we just repeat k times, let's say. You do this again and again and again. So very simple stochastic gradient descent. Now let's see how to privatize this. How would we privatize this? Well, there's only one algorithm I've taught you so far, which is adding Gaussian noise. And so you'll want to add Gaussian noise to this gradient. Now the issue is the fact that this has unbounded sensitivity. That is, these gradients could be any value. They could be very, very large. They could be very, very small, and so on. So we're going to have to do an additional step which clips the points, clips the gradients. So let's this might be a lot. So let's take this step by step. So this here is differentially private stochastic gradient descent, which was kind of proposed in a line of works at various levels of maturity, in the sense that perhaps the paper to first introduce it was maybe Song, Chowdhury, and Sarwate for the stochastic version. Basili Smith-Thakurtha, they did a very thorough theoretical analysis, and this Abadi et al. Paper was instrumental in getting a practically usable version of DPSGD, as we call it. So how does it work? Well, the first thing we're going to do is, instead of sampling a mini batch of points, what we're going to do is sample a lot of points, where we pick each point to be in this lot with probability L over N. This will be about L points if you sample from the whole overall data set. Now, this is already a bit of a departure from the standard algorithm, where we just pick some arbitrary batch. It doesn't matter too much. But this differs in the sense that we sample randomly like this with a very specific scheme, and this is for privacy reasons, which I'll mention in the next slide. And this is kind of the key, most instrumental part. So what we're going to do is we're going to, for each point in the lot, compute the gradient. This is exactly what we did before. But the difference here is now, like I said, before these could have been arbitrarily large. And so what we're going to do is we're going to clip our gradients in order to have L2 norm at most C. So as an illustration, C, like here's this ball I drew earlier, which is a ball of radius C, and suppose we have some gradient vector which is bigger than this. Well, what we're going to do is we're going to clip that gradient and say, okay, you have to lie within this ball. And this is convenient for reasons which I showed you in a few slides ago, where if we know that all of our gradients are going to be within this ball, then we can bound the sensitivity of the function, saying that, okay, we have sensitivity at most 2C. So now that we have these clipped gradients, what we can do is we can average the clipped gradients and we add Gaussian noise. This is exactly an application of the Gaussian mechanism, or the Gaussian algorithm, that we mentioned a few slides ago. So because we have bounded sensitivity, and if we add appropriately calibrated Gaussian noise, then therefore this will be private. Then we take a step in the negative direction of the resulting vector, which is not just going to be the empirical gradient, it's going to be the empirical noise gradient, or the empirical clipped and noise gradient. And finally, again, we just repeat k times. So as you can see, this is fairly similar to the regular SGD algorithm. The main differences are that we clip the gradients and then we add Gaussian noise proportional to this clipping norm. Those are the main differences. It's pretty much the same otherwise. So this is a very convenient and nice and drop-in replacement for SGD. As you know, that SGD is used to train a lot of machine learning models. And so therefore, any place you could just swap this in and it'll give you something. Now, the question you'll be asking is, okay, you can do this, but first of all, one, is it private? And two, is it accurate? So let's address these both one by one. First of all, how do you even analyze this privately? Well, so the first thing that we'll note is, I'll do an informal analysis of it. The real privacy analysis can be more technical. But the idea is we're going to use the privacy of the Gaussian mechanism. Then we're going to use composition over all these steps we do in differential and DPSGD. And then finally, we're going to also use something known as privacy amplification by subsampling, which is not something which I mentioned. But okay, so the point is, first of all, though, suppose this should really say one application of the Gaussian mechanism has privacy with parameter epsilon. We basically set this step here, step 3, such that this Gaussian noise addition would be epsilon dp. We're going to ignore the deltas just for sake of explanation. Well, the first thing you do is remember this first step where you subsampled points. Each point was chosen to be in your data set for this mini batch, or this lot as we called it, with probability L over N. So there's some property of differential privacy which is a little bit more technical, which I'm not going to get into, which is called privacy amplification by subsampling. So then you can argue that each step is in fact epsilon times L over N. So we kind of scaled down this privacy parameter by a significant factor if N is large and L is not too large. So that's one thing. Then we can say that each step has a stronger differential privacy. And then the last thing is that since we had k steps, then outputting the result of taking k steps would have basically, by advanced composition, epsilon times square root k times L over n differential privacy. Now, you might be wondering, why did we have to pay for all k steps? Like, if when you're doing SGD, maybe DPSGD, you only output the very final result. You only output the result of the final step. So maybe it should only have epsilon times L over n. But no, because each of these steps in DPSGD depends on the previous step, and so it's the privacy is kind of leaked as a result. So in fact, this root k really needs to be here in that sense. So this is a bit of I didn't talk about a lot of details, but this is kind of how the analysis works, just privacy amplification by subsampling and advanced composition. In fact, there's even more better analysis that you can do using something known as moment accountant, which was introduced in this paper by Abadi et al. And that, in terms of like, this will give you sort of the right analysis up to constant factors, but in terms of the actual privacy guarantees, getting like usable privacy, constant factors don't mean much when we're talking about the epsilon, because there's a big difference between epsilon equals 1 versus the epsilon equals 10. So if you want to get better, closer to the tight analysis, you have to use something called moments accountant. And you can see that this is kind of the advantage in privacy that it gives you. Whereas you can see that the white boxes are going to be what you would get via using strong composition, kind of this analysis that I sketched out above. But if you use this better analysis, you'll get something which is only constant factors, but quite significantly better in terms of actual privacy guarantees. For example, if you look all the way over here at 350 epochs, you're going to have epsilon equals less than 5 versus epsilon greater than 20. And these are very different privacy guarantees. So there's a lot of math if you want to actually get the right guarantee here. Now, that says if it's private or not. The next thing you might be wondering, does it work? Is it any good? And here's a figure from Tremer and Bonnet 21. This is kind of like one of the state-of-the-art results right now. And the answer is kind of, I mean, yeah, like let's take a look at this. There's 3 different data sets which are mentioned here. First of all is MNIST, which you should be familiar with. This is a relatively easy data set, and you can see, okay, the non-private accuracy we can get on this is like 99.9 whatever. And you can see here that the column you should be looking at in terms of or just look at the bold things for, I guess, the best accuracies that we currently know of. And you can see with reasonable privacy guarantees, 1, 2, 3, we can get something like 98.1, 98.7, stuff like this. These are pretty good. I think if you tell very simple methods, nonetheless, get non-privately get accuracies of 99%. Or basically anything works on MNIST, but like 98.7 doing it with privacy is not bad. The thing is, this is relatively an easy data set. And when you move to harder data sets, for example, fashion MNIST, you can not even get 90% with privacy, really. Whereas, of course, state-of-the-art methods can get 99% plus. And this is especially true when you move to a harder challenge, such as CFAR 10, which is kind of the hardest thing that people have looked at, the hardest benchmark data set, let's say, that people have looked at with differential privacy. And you can see that it's a paltry 69% is kind of the state-of-the-art right now, which is not great in the sense that any practitioner would tell you that this is too much accuracy loss in order to be useful. Whereas, meanwhile, again, for CFAR 10 non-privately, we can get, say, 99% plus. So it works for some maybe basic tasks. It can get pretty good accuracy, but in terms of more complicated tasks, it seems that this is still a challenge. Cool. And I'll conclude just by telling you a few other things which come up in differential privacy, which didn't come up before. There's just a few more differences. There's a few more differences and a lot more considerations that come up in differentially private machine learning. So one thing is that differentially private SGD can be slow. For example, you can see some plots here on running on an LSTM network, where if you just try to run DPSGD naively, under the top are the runtimes under privacy, and the bottom are the runtimes without privacy. And you can see that many of the popular libraries for privacy, say what's known as TensorFlow privacy, for example, they incur large runtime overheads, whereas compared to, say, the non-private runtimes, which are much less. And this is the reason for this is because there's some operations which you need in DPSGD which weren't really optimized in the non-private setting. For example, you need to be able to compute per example gradients. For each individual gradient, you need to be able to clip it individually. Now, in the non-private setting, this isn't really something you generally need to do. So it hasn't been optimized, and you don't really have access to these objects, and therefore, in the kind of for DPSGD, you typically have to do it sequentially. Just basically, you can't use things like GPU accelerators and stuff like that in order to speed things up. Now, there are some sort of hacks and ways to get around it, but it seems like certain different tools, for example, JAX is one recent framework, which is very good at doing these per example gradients and can essentially help reduce these overheads due to privacy. So these are just some sort of the hardware differences which result in differential privacy being much slower in practice. And this type of overhead has been noticed before. For example, some people complaining that things which take maybe like 10 minutes without privacy will take upwards of 10 hours with privacy. So you have to really use the right tools for the job in order to get rid of these overheads. And this would work with Subramanian Vadivelu. Another thing is the architectures for DPSGD for privacy are kind of different for a number of reasons. So one difference, for example, as Paperno, Thakurtha, Song, Xian, and Erlingson showed, sometimes we have to switch our activation functions. For example, ReLU is kind of the most popular activation function nowadays in deep learning and machine learning. And they showed in this, they gave some compelling evidence that perhaps the tanh function might be a better one to use for when you're doing differential privacy. It produces better empirical results. Tanh was typically considered to be one which is not really used anymore in modern machine learning just because of issues we talked about related to, say, exploding and vanishing gradients. But in the differentially private setting, for certain reasons, it seems like empirically it could be better. Another significant thing is the fact that bigger models are not always better. Typically in the non-private setting, when you have more parameters, then the model will become more powerful, and it seems to just generally do better, even when it has many, many more parameters than training data points. However, this is not the case in the private setting. The reason is because, remember when I said that we add noise to each coordinate of the function? Well, when you're doing that in the private setting for neural networks, adding noise to each coordinate means essentially noising in each coordinate of the gradient. And the gradient will have one dimension for each parameter. Therefore, if you have a very, very high dimensional gradient, then in fact, you'll be adding noise, which is proportional to the square root of the number of parameters, essentially. Therefore, you kind of want some trade-off. The bigger a model, then maybe the more expressive it'll be, but also the bigger model, then the more noise you will have to add as well. So you kind of want to find some sweet spot where those two balance out. As a final thing I'll mention is hyperparameter tuning, where hyperparameters, you've probably learned, have a pretty big impact on the effectiveness of a algorithm. But the thing is, first of all, there's even more hyperparameters in the differentially private setting. Here's a few, which I haven't really talked about all of these, but these play into the running of the algorithm. But more troublingly, it's just not clear how to even do this hyperparameter tuning in a differentially private way, in a sense that in the non-private way, sometimes you would do your hyperparameter tuning by just like doing a grid search, maybe running every algorithm, measuring the accuracy on the validation set, and so on. However, this won't really work in the private setting because you're essentially, if you tried all your hyperparameters in your grid search over the possible hyperparameter sets, then you're essentially doing one query on the sensitive data set for each of these different hyperparameters, and therefore composition would mean that you have to pay for all of them. You don't just get them for free. Somehow every one of them will leak some information about the training data, and that will reveal something. And essentially, yeah, like what I'm saying is you have to pay for a privacy budget in each run. And there's a number of options on how to get around this. How do you avoid paying for essentially this hyperparameter tuning stage? Well, there's some ways, which, for example, private methods for hyperparameter optimization. Say one theoretical work was shown by Liu and Talwar, which kind of makes it works in theory, but I don't think it's been explored too much in practice as a real method. Another thing is to transfer hyperparameters from related public data. For example, just do all the training you want on some public data set, and then once you figure out good parameters, hyperparameters, then you can run it on your sensitive data set in just one go. Sadly, the most common thing in practice is that people typically just ignore this cost. They just do hyperparameter tuning. They ignore the fact that they did this tuning in a non-private way. And then they just finally report what the privacy would be just due to that final run, which is, in my opinion, kind of cheating, but it's what people do nonetheless. All right, so that's all I want to talk about today. The kind of takeaway I want is that there exists private machine learning, basically methods which are good at preserving privacy in machine learning. But there's still a lot of work to do. There's a number of new challenges that come up, and it's not perfect yet. But I think it's a promising direction right now, and hopefully we can improve these methods over the next several years.